Hello, welcome back. I'm Jason with mathandscience.com. Today, the title of this lesson is called Logarithm Change of Base Formula and also solving more exponential and logarithm equations. I told you at the very beginning, the most important thing about logarithms that we're going to use them for, at least in the near term, is in solving equations, specifically solving exponential equations. And we have solved some exponential equations and we have used logarithms. But by now you probably figured out that some equations become difficult to solve if the logarithms, or to get a numerical answer for it, if the logarithms that you're dealing with are in crazy weird bases. Like for instance, we've talked about the fact that you can have logarithms in a base 2. You can have base 5 logarithms, base 3 logarithms. So you have those exact answers if you can take logarithms with all these different bases. But a lot of times what happens is you have a calculator in your hand and you want a number. But the calculator doesn't have usually a logarithm with a base 5 and a base 6 and a base 10 and a base 11. They usually don't have all of those things. So how do we evaluate and solve equations to get numerical answers when the only button on the calculator we have is the regular logarithm button? How do we do that? So it turns out that there is what we call a logarithm change of base formula. And that is a really neat little tool to have in your back pocket because it allows you to take logarithms of any base you want by changing the way that the problem looks. And it's a little bit complicated to say in words, so I'm going to write it down for you. Before we get to the actual change of base formula, I want you to kind of just pull your calculator out, whatever little calculator you have. Generally, there's going to be 2 logarithm buttons on the calculator, okay? The first one will be called log. If you just see an log, a log button, it means it's a base 10 logarithm. You don't have to put the number 10 there, the little base 10 there, because you know if it says log, it's base 10. So log on your calculator means base 10, right? And then you have another button that's called ln, and this thing's called base, it's called a natural logarithm, and this is a base e. Logarithm. We're going to study base E natural logarithms later. I don't want to get into it now, but just suffice to say there's a very special base labeled with the letter E, and that is just a number. E is a rational number like pi or like square root of 2. E is 2.71 and then infinite non-repeating decimals after it. We're going to get all into why E is important a little bit later. So forget about it for now, but I want to just let you know that your calculator is only going to have 2 buttons, base 10 logarithm and base E logarithm, right? Now computer, if you go to a computer, you can take any base logarithm you want, but on a handheld calculator, these are the only ones you'll probably see. So how do we do something, for instance, like if I want to figure out, what is the logarithm base 4 of the number 17? How do I do that? Like how do I even type it into the calculator? There is no way to do usually logarithms of different bases in a calculator. So we have a formula that I'm going to write on the board that's in all of the algebra books. It's also in the calculus books because we use it quite a bit in calculus. And it's called the change of base formula. So let me write it down and explain how it basically works. All right, so this is the meat and potatoes of this lesson. This is called the log change of base formula. And you're going to find out that it allows us to do things like this actually really, really easily, all right? And here's what it is. It's not very hard or lengthy to write down. Here's what it is. Logarithm base a of the number x, any base I want, can be written as the logarithm of any other base I want of the number x, same as this, divided by logarithm, same base b, of a. Now, I'm fully aware that most of you that have never seen this before are going to look at this and say, this makes no sense to me. So here in just a minute, it will make a lot of sense, I promise you, right? But what it allows you to do is it allows you to take logarithms of crazy weird bases only by using, well, it's used for more than this, but mostly you're using it to be able to do it on a calculator because you don't have base 15 logarithms or base 7 logarithm buttons on your calculator. I am not going to prove this right now here in the beginning of the lesson. What I want to do is show you how to use it. And then if you stick with me to the very end of the lesson, I'm going to derive and show you where exactly this thing comes from. So just stick around if you want to know where it comes from. Now what this is saying, in a nutshell, it's easier to see with a simple little example. What if I wanted to take the logarithm, right? the base 3 logarithm of the number 9. Now, I just told you that the base 3 logarithm button is not in your calculator, so there's no way to put it in there. So you can see log base a of the number x. This is log, in this case, base a is the number 3, and the number I'm taking the log is here. So this is basically this. What this is saying is I can write this logarithm as follows. I can change the base of this logarithm from base a to any other base I want. Notice b is the base on the right and a is the base on the left. So if I want to, I can change this thing to a logarithm base 2 of the number 9 divided by logarithm base 2 of the number 3. I want to let that sink in for a second. What it's saying is I'm trying to take base 3 log of the number 9. I can instead change that to the logarithm of the number 9. What originally you're taking the log of over here, you're taking the log over here. I want to make it a base 2 for whatever reason. So I have to take base 2 logarithm of 9, but then I have to divide it by the base 2 log of what the original base is. See, the base is 3 right here. Okay. Now this isn't so helpful because I don't have a base 2 logarithm on my calculator either. I don't have a base 2 button on my calculator. But mathematically, a base 2 log of 9 divided by a base 2 log of 3 is equal to this right here. Now you can make any base up on the right hand side that you want. For instance, it doesn't have to be base 2. I can make this log base 7 of the number 9 as long as I divide it by log base 7 of the number 3. You see what I've done? I'm still taking the log of 9. I'm still taking the log of the base, but now I've changed it to a log base 7. Now, the real reason that we use this thing so much is for the following. All right, because I can make it log base 10 of the number 9, log base 10 of the number 3. So you see, in other words, I can transform this log into a division of 2 other logs of any base that I want. I just have to take the log of this thing and the log of this thing. If I want base 17, no problem. I can make it log base 17 of 9 divided by log base 17 of 3. If I want base 24, I can make log base 24 of 9 divided by log base 24 of 3. Of course, I don't have buttons for all those other weird bases, but mathematically they're correct. Now, why do I care about base 10 so much? Right? Because basically this means this is the same as log of 9 divided by log of 3. There is an implied base 10 here because when you don't write it, you just assume it's a base 10. Now, I do have a logarithm base 10 button on my calculator. In fact, that's why we don't usually on handheld calculators have crazy weird base buttons or menus or anything to be able to take logs of different bases, because you don't need to. If you need to take a crazy log with a crazy base, just transform it to be a log base 10 of this divided by a log base 10 of this. So the way you want to read this transformation of bases, this log can be written as log of this divided by log of this in whatever base that I want. Usually you're just going to convert it to base 10 in order to do the calculations. Okay, let me show you a practical example of why you might want to do that. Let's say you have log base, let's make it base 4 of the number 7, and I want you to simplify that. Tell me what that's equal to. Well, you all know that if I wanted to, I can use the definition of logarithm to try and solve this. I can say base to some number equal x on the right-hand side of the equal sign is equal to 7. This is what we've been doing for the definition of all logarithms. 4 to the power of something is equal to 7. That's typically how I've taught you how to solve logarithms. You write it as an exponential, and then you try to figure out what this exponent is. However, 4 and 7 have completely different bases. I cannot write them on the left and the right-hand side as the same base. I can't do it. So there's no way that I can solve that thing. Right? However, let's just abandon that and let's go down here and say, okay, instead of evaluating it by using the definition of the logarithm, let's just change the base. Right? What this means is that instead of log base 4 log of the number 7, I can write this as the log of this divided by the log of this in any base that I want. So I can just make it a base 10 log of the number 7 divided by the base 10 log of the number 4. I have buttons for these on my calculator. Now, of course, I could make this a base 9 log of 7 and divide by a base 9 log of 4. Or I can make this a base 2 log, divide by a base 2 log. All of them are correct. You can pick anything you want, but base 10 is the only thing I have a button for. So on my calculator, I'm going to go crank in and put log 7, and I'll get a decimal back, 0.8 451. This is rounded and truncated, of course. I'm just carrying 4 decimals. And then 0.6021. And so when you put that in and do that division, you'll get 1.404. Again, it says rounded, right? Right? So I can say that the log base 4 logarithm of the number 7 is equal to this, and I can do it in my calculator because of the change of base formula. Now, if I wanted to, instead of doing it like this, I could also say, okay, well, I'll do, I could do log base 2 of 7 divided by log base 2 of 4, right? If I calculate this, it's going to get exactly the same number. Or I could say log base 3 of 7 divided by log base 3 of 4. See, you're just taking the log of this divided by the log of this in any base you want. That's what the change of base formula is. It's kind of hard to see the power of that here. There's a bunch of letters everywhere. That's why I kind of write it on the board, and then I immediately want to get away from it, because when you look at all the letters, they all get confusing. But when you see real problems, you can see how important and how useful it is because of what we're doing here. All right, now remember, a long time ago, way in the beginning, I told you one of the biggest uses of logarithms was to solve exponential equations. So how about something like this? 3 to the power of 2x is equal to 5, right? So this is an exponential equation. If you're a human computer and can guess the power of x here, needed to make it equal 5 when you raise it, then you are much, much smarter than me. And there's a lot of people that are way smarter than me, so good for you. But most of us can't calculate like that. So how would we solve this? We're going to take log of both sides. Why am I going to take the log of both sides? Because I know that a logarithm with a base 3 can cancel this exponential entirely. So for instance, I can make this log base 3 of 3 to the power of 2x. That's what I'm taking the log of. And if I do it to the left, I also have to do it to the right. I can do whatever I want to both sides of the equal sign. So since I have a base 3 logarithm and I'm taking the log of a base 3 exponential, they cancel. All I have left on the left is 2x. And I still have this log 3 of the number 5 on the right-hand side. No problem, okay? So what I want to do is I want to figure out how to solve this thing. But the problem is I have now a base 3, even though I did this and it's like, okay, cool, I've got this. I've got a logarithm down here. But I don't have a base 3 logarithm button on my calculator, so I'm stuck. Now, if I want to write it exactly, I could just divide by 2 and say that's the final answer. I could just say, well, x is log base 3 of the number 5 divided by 2. This is the exact answer. Of course, I can circle that, but the problem is, what if you want a decimal? What if you're trying to calculate the tolerance and all of some part in a design, and you only need 3 decimals of accuracy? Well, then you want a number. You don't want to leave it as a weird logarithm. So what you would do is you would take this step right here, and you would go over here, and you say, well, I know that 2x is the log base 3 of the number 5. I don't have a button like this, but I know I can change base. I can say this is the log base 10 of the number 5 divided by log base 10 of the number 3. Again, I'm choosing base 10 here only because I have a button on my calculator that's a base 10. I could easily say base 4 log of 5, base 4 log of 3, base 2 log of 5, base 2 log of 3. They're all correct, but none of them are useful. So I'm trying to tell you what's basically useful. And so then if you want to get the value of x here exactly, you could say log base 5 divided by the 2 times the log base 10 log of 5 base 10 log of 3. Now I can circle this and call this exact. At least I have base 10 logarithms there. But the problem is, generally you want numbers. So you could say x is equal to, what is the base 10 log of 5? 0.6990. Of course, that's rounded. And then here you have 2 times, what's the log of 3 is 0.4771. So when you crank this to a calculator and divide by 2, divide by the 0.4771, you'll get 0.7326. Again, this is rounded. These are all rounded numbers because when you take logarithms of weird numbers like that, you're always going to get, infinite decimal. Not always, but almost always infinite long trailing decimal. So I'm just rounding it here, 7326. So before knowing the change of base formula, you'd basically be stuck right here. You would know you could take the log of both sides, but you'd be stuck. You could solve for x, you could get it to this point, but you wouldn't know how to actually take the log of this because of the way the numbers are. I mean, you could use the definition of logarithm and say 3 to the power something is 5, but what is that power? You still don't know how to solve that because 3 and 5 are weird numbers. You can't put them in the same base. So this is one of the primary uses of this change of base formula. It looks a little bit weird in this format, but when you crank through it, you can see how useful it is in solving equations. Now, what we're going to do for the rest of the lesson is I'll do a little bit of a mixture of solving some more exponential equations, solving some logarithmic equations. Sometimes we'll need the change of base formula and sometimes we won't. And at the end of the lesson, I'm going to derive this change of base formula. It's only about 5 lines of math, but I do want you to know where it comes from. So it's not a crazy long derivation. All right, let's say we have logarithm x equals 0.8531. Now, when you see logarithm of x and there's no base here, you need to assume it's a base 10. You need to get used to that. When you don't see anything there, it means base 10. Now, how do I solve this? Well, I can use the definition. There's a base 10 here. It means 10 to the power of this, 0.8531, is equal to what's on the left-hand side. So when you flip it around, you can say in calculator 10 to the power of whatever this decimal is, you'll get 7.130. Again, this is rounded. This is the value of x. These are little kind of short, simple little problems just to show you that when you have decimals, you can put them in your calculator, raise it to the power of 10. You can take logarithms with decimals and things. It's kind of trying to get you to start using your calculator because sometimes you will almost certainly need to use a calculator to finish the problem off. What if you have logarithm of the number x is equal to negative 1.8? Now again, there's no base here, so that means you need to assume it's a base 10. So the way you solve this is you say base 10 to the power of negative 1.8 is equal to what's on the left-hand side, x. So then you go to your calculator, stick negative 1.8, raise 10 to the power of that. Should be a button on your scientific calculator to take 10 and raise it to the power of something. And you will get 0.0158. Again, this is rounded, 0.158. All right? We just have 2 more of these small problems, and then we're going to derive the change of base formula. What about 3 to the power of x is 30? Now, this is an exponential equation. How would you solve it? Well, in order to get rid of the exponential here and get this x off by itself, I need to get rid of the exponential, so I'm going to take the logarithm of both sides. But if I'm going to take the log of both sides and kill this, it needs to be a base 3 logarithm. 3 to the power of x. Base 3 logarithm on the right of the number 30. Base 3 logarithm on both sides. So when you actually do that, the logarithm and the exponential cancel, just leaving you with the variable x, equals log base 3 of 30. Now, up until now, you would just circle this as your answer, a log base 3 of 30. That's totally fine. However, what if you want a decimal? How would you calculate it in a calculator? We're going to use the change of base formula. So what you'll get is you'll say, well, this is a logarithm, base 10 log of this, 30, divided by the base 10 logarithm of the base, 3. Again, I can use any base I want here. I can use base 7, base 10, base 14, base 20. It doesn't matter, but base 10 is the only one I'm going to use because that's the button on my calculator I have. So the base 10 log of 30 comes out to be 1.477. This is rounded. Okay. Yeah, I guess I'll do it like this. And then on the bottom, you'll have a log of 3, 0.477. And so then what you'll find is x is equal to, when you take those numbers and divide, you'll get 3.096. Of course, this is approximate again because this is an approximation. This number is exact. So if you were asked to tell me the exact value of x, this is what I would write down. Now you could leave it like this, sure. But generally, you want to convert to base 10 so that somebody else could finish the calculation and use the change of base formula to get there. This is the exact value. This is acceptable also. But in base 10, this is the exact value. And then, of course, you get the numerical approximation to it. All right? Now, what we want to do is we want to show you where things come from. I want to show you where this change of base formula comes from. It's not a hard derivation. It only takes a few seconds. But then you'll feel comfortable knowing where everything comes from. So what I want to do first is I want to make a definition. I'm going to say let the following thing be true. Logarithm base a of some number x is equal to y. I can, in a proof, I can let anything equal, in my initial step, I can let anything equal. I'm just assigning letters, basically. I'm saying a base A logarithm of some number x is equal to some number y. Of course, I can make any assignment I want. But if I make that association, then you have some consequences of that. If I make that association, then I say that a to the power of y is x. How do I know that? Because the base to the power of this is equal to this. That's just the definition of the logarithm. Then I can say, I can do whatever I want to this, because if this is true, then this is true. So then the next thing I want to do is I want to try to take the logarithm of both sides, right? And in order to keep everything general, I'm going to take some logarithm of both sides, but I'm going to take it with a different base b. Here's a to the y power log base b of x. Now, you might say, well, how do you know to do that? Well, the truth is this is a proof. Nobody here watching this, I expect, to really know how to prove this ahead of time. You probably see this thing one time and say, oh, I get it, okay. So you're not going to really know ahead of time that this is going to work, but I'll tell you the reason I'm taking a log with some other base b is because I know that where I'm trying to get to has a logarithm with a base b over here, and then I'm starting with a logarithm of some other different base a. So the only way I'm going to really be able to get to proving that thing is to introduce a base b logarithm somewhere, and I know it's legal to take the logarithm of both sides of an equation anytime I want. So I'm going to do that. Now here you can see you have a logarithm here, but this exponent can come out with the law of exponents. So y times log base b of whatever's left over a. And this is log base b of x. All I've done is using the law of logarithms here. But here's the thing. I know what y is equal to. Y is equal by definition to this line up here, so I can substitute that in. The log base a of the number x multiplied by the log base b of the number a is equal to log base b of the number x, right? And so basically, believe it or not, we're actually home free. Let me just solve for this term. Log base a of some number x is equal to log base b of some number x divided by log base b of some number a. This is what I've proved. I've basically said the logarithm with some base a of some number x is equal to the log of x divided by the log of the base in any other base I want. This right here is exactly what I wrote on the board here, right? So we've proved that guy. Now, do I expect you to care about that? Do I expect you to write that, you know, down every night and cuddle up to it and love it? No, of course not. But I want you to know where things come from. I want you to know that they just don't come down from the sky. And I also want you to know that something as weird looking as this formula is not that hard to understand. I mean, yes, if you don't know what a log is, it looks hard, but it's a very logical set of steps. I'm letting this equal to this. This is the definition of the logarithm. I take the log of both sides. I use the law of logarithms to pull it out. And then from then, I just rearrange and figure out this is true. This is very useful. You would use it in algebra, you would use it in trig, you would use it in calculus extensively. It's called the change of base formula. So make sure you understand how to solve all of these problems. Follow me on to the next lesson. We'll get some more practice with solving more exponential equations and using the change of base formula of logarithms.